Okay, so let me talk about the final exam, which is next week. We'll start here at 6:45, and it'll go 3 hours. I guess if you want to stay until 10 o'clock, that's fine. But it shouldn't take that long, okay? It is a long test, but 3 hours is more than enough time, in my opinion. It's going to be all multiple choice. It will have a section of conceptual questions related to hypothesis testing, confidence intervals, that kind of stuff. A section asking you which is the appropriate test to use in this scenario. So I'll list off a few scenarios, and you need to tell me which one is the correct test to use. So between those two sections, that will probably be around 15 questions. So I would say, yeah, 10 conceptual questions, 5 questions on which tests to use. And then there will be a whole bunch of questions where you do the actual tests and answer related questions. So it'll be like each page I'll present some data or a description of some study, and then I'll ask you, in this situation, I'll say, do this test, and I'll say, what are the appropriate hypotheses to use? So make sure you know, for each test, you should know the appropriate hypotheses to set up. You should know how to calculate the test statistic and p-value for each test. You should know what your conclusions mean, the interpretation of the conclusions for each of those tests. Okay, so you'll have a series of questions, just with different scenarios, asking you to work through tests. And then I just have just a couple or a few miscellaneous random questions that related to the class. They should not pose much of a threat. Probably 3 or 4 questions there. Okay. The exam is about 55-ish questions long, something around there. And I'll probably grade it out of 51 or 52 questions or something, so that there will be a few extra bonus questions. So if you answer them all right, you'll get over 100%. Is that okay? You are allowed a note sheet, writing on the front and back. Please bring your reference tables. And make sure your calculator works. I will provide Scantrons. That's that. I will not have office hours the day of the final. Okay, so I'll just show up a little bit before 6:45 to pass out the tests, and you guys can take them. Okay. I'm going to, I'll try to get your quizzes graded as quickly as I can, and I will try to send you a progress report with all of your grades before the final exam. Okay? And so it will have all of your grades calculated. I'm going to drop the lowest of the 4 quiz grades, so that will already be calculated in this progress report. And so we'll have everything except for the final exam. And then I'll go ahead and do some calculations for you guys along the lines of, if you want an A in the class, you need to get this on the final. If you want a B in the class, you need to get this on the final, etc., etc. Okay? And so then you should have a clear idea what you need. Some of you guys are doing very well. So it will say if you want an A, you only need to score like a 75 on the final or something. Okay? But don't take that as a reason to blow off studying. I think the final exam is fair, very fair, but there is quite a bit that we covered in the class, so it would do you well to look over this stuff. Yes.
Is it cumulative, or are you heavily focused on the last one?
Yeah, heavily focused on stuff from, I would say, chapters 7 and okay. So chapter 7 through 12, heavy focus there. I'm trying to think. I might just have a couple questions, general questions. Like I said, maybe three questions or so from prior to that, or just related to the course. Things I don't know. Maybe just some what is statistics about type of thing. If I say, I'm trying to think of a question that is similar to one of these questions. It's not exactly the same, but I don't know. Something like that. Okay. I wouldn't stress too much about those. Other questions? Yes.
How would you best, or like suggest study for the conceptual questions? Because I know on the last midterm there was some that were like straight from the book. So the conceptual questions would be coming from the book?
So I'm going to cover chapter 12 today, and then I'll spend some time in review today, and I'll go over some conceptual topics there. I guess regarding the conceptual questions, make sure you really understand definitions of the p-value, okay? What how can I give you ideas without giving away the actual questions? So definitely know, the definition of the p-value and I guess in a certain context, what does it mean to get a p-value of this amount? So if you do a hypothesis test and you get a p-value of 0.12, what does that mean? Okay, and so getting a p-value of 0.12, well, it could mean several things, but you should know them all. It means generally, if you're using alpha 5%, your p-value would be larger than alpha, so you would not reject the null. P-value of 0.12 means that if you assume that the null hypothesis were true, the probability of observing your data or something more extreme is 12%. That would, and you should know, in the context of a particular problem, what that means. Know your error types, type 1 and type 2 error, and how that plays into your selection of alpha. So we talked about that, right? So think of like the smoke detector versus the jury trial.
What about beta?
So we don't choose beta, but you should know how alpha and beta are related. Okay, so beta is related to type 2 error, and using the same data, a larger alpha corresponds to a smaller beta, and a smaller alpha corresponds to a larger beta. Conceptual things like that. Yes?
Sorry, you've already answered this. So do we get a cheat sheet or cheat card?
Yes, you are allowed a full letter size sheet of paper, writing on the front and back, okay? And bring your reference tables as well, okay? So during the final, I'll come around and I'll just do a quick check, just make sure that everybody just has one sheet of paper and things like that. Trying to think, anything else? So yeah, other conceptual questions. Oh yeah, how confidence intervals are related to hypothesis tests. Well, the confidence interval and the t-test, how those two are related. Interpretations of the confidence interval. Okay, what does it mean to have 90% confidence interval? Or proper interpretation of a confidence interval. So all the conceptual ones are basically interpretations of the results of statistical tests and inference. Okay, so we spent a lot of time going over tests and how to do them, but just as important is the making sure we can interpret them properly. Okay, and then again, you have and last week we went over how to choose the appropriate test, and that's also important. So, okay. Anything else regarding the final? We're feeling okay, more or less. All right. Well, I'll start going over chapter 12, and then we'll take a break, and then I'll spend the rest of the time in review. Oh, and then we also have to do, before we take the break, remind me to do instructor evaluations if I don't remember that. Okay. So chapter 12 is all about correlation and regression. And in this class, we are only spending this week, and we're only going to learn the most basic form of regression, linear regression. And regression, correlation regression, this applies anytime you're trying to make a relationship between numeric variables, okay? Is there a relationship between numeric variables? So all the other tests we've learned in this class involved a categorical variable, either two categorical variables, or a categorical variable by itself, or a categorical variable and a numeric variable. And regression, this is the last one, this is the one where we have two numeric variables. If you have two numeric variables, you will have to use correlation and regression. Okay. So use this when we have two numeric variables. Like ANOVA, like other topics that we've touched on in this class, you can spend a lot of time or go take an entire course on regression. You can spend your entire life researching regression and learning all the different forms of regression. Here we are just learning the most basic form of regression, which is linear regression. But there's multiple regression, non-linear regression, all sorts of stuff going on. We're just learning the most basic form. Okay. So correlation and regression. Okay, so let's talk about correlation and regression. Let's say we've collected information. We have two numeric variables, and so a simple example that the book uses is that for a particular species of snake, we can look at, so we're looking at snakes, and we can look at the length of the snake and the weight of the snake. Let's see. Let me get these. So for a particular, this is for one species. We look at the length in centimeters. So they have here, one snake is 60 centimeters, so about 2 feet long, and it weighs 136 grams. Okay. And then another snake was 69 centimeters long and weighed 198 grams. And another one was 66 centimeters and weighed 194. And so on and so forth. We'll collect more and more data. All we want to know, is there a relationship between the length of the snake and the weight of the snake? Okay. And so if you just picture how snakes are in your mind, maybe you don't like snakes, so I apologize for making you picture this. You can just imagine that longer snakes weigh more than shorter snakes, okay? It's like snakes are like pieces of rope, and it's basically you're just cutting a longer piece of rope, you're going to have, it's going to weigh more, okay? But yes, you know, there's going to be individual differences. Some snakes, even within the same species, maybe some of them are, you know, fatter or skinnier, and so maybe you have a snake that's longer that doesn't weigh that much more, or it weighs less than another snake. But overall, we would probably see this overall relationship where we see longer snakes will tend to weigh more than shorter snakes. A basic tool for exploring relationships between numeric variables is the scatter plot. Scatter plot has an x-axis and a y-axis, and we just plot numbers on these axes. Okay, so So that first snake, which is 60 centimeters long and weighs 136 grams, would have a dot somewhere around here. So we're just plotting these as coordinate pairs. We have another snake that's 69 centimeters and weighs 198 grams. So that snake would have a dot somewhere around there. And then we have a snake that's 66 centimeters and weighs 194 grams. So it probably has a dot somewhere around there. And as we gather more data, we might see different snakes kind of like that. And we may try to fit a line to describe the overall relationship. Something like that. But a scatter plot is just showing, plotting each point as a coordinate pair on there, okay? And it's very important that we make a scatter plot, okay? Because by using just numeric summaries, such as finding the mean length and the standard deviation of the length, and the mean weight and the standard deviation of the weight, and even calculating correlation, which we'll talk about in a minute here, looking at numeric summaries alone will not give us an idea of whether or not the two things are related, okay? So looking only at numeric summaries. Mean, standard deviation, correlation. Will not tell us if the variables have a relationship. We should make a scatter plot. So let us see the data. Okay. So we can, when we create scatter plots, and we're graphing numeric variables, we can talk about the relationship that exists. And so when describing a relationship, there are a few things we want to mention. Okay, so first we want to mention the form of the relationship. Form or shape. And as far as this class goes, it's either the relationship is linear or nonlinear. Okay. Nonlinear is just a catch-all for anything that's not linear. I guess if you learn more regression, you could have more details on that. But linear just means a straight line is a suitable approximation. So the snake's length of the snake and weight of a snake, a straight line seems to encompass that overall relationship pretty well. And we see longer snakes tend to weigh more, shorter snakes tend to weigh less. Nonlinear would be anything where maybe your scatter plots look something like that, okay? So a straight line doesn't quite capture what's happening with the data. Okay, these are extreme examples, but here a straight line would not work. I mean, if I tried to put a straight line, maybe it would look like that or something. So these would be nonlinear relationships. So as far as linear relationships go, if the relationship is linear, we can start talking about the direction and the strength of the relationship. So other things to mention when describing a relationship, we want to talk about the direction of the relationship, and the strength of the relationship. So the direction of the relationship can have a positive relationship or a negative relationship, negative direction. Okay. Positive relationship things that look like that. Larger values of x correspond to larger values of y. And smaller values of x go with smaller values of y. Okay. So the snake's length and weight, positive relationship. Longer snakes, so high values of x, correspond to heavier snakes, high values of y. Shorter snakes, small values of x, go with lighter, correspond to lighter weights, so smaller values of y. So large x goes with big y, large y, small x goes with small y. Negative relationship, just the opposite. Okay? Things go like that, so you have large x goes with small y, and small x goes with large y, and vice versa. Okay. So what might have a negative relationship? Think of two numeric variables, maybe that have a negative relationship. Yeah.
Eating and losing weight.
Okay, so the amount of food consumed
Yeah.
and the amount of weight lost. Okay, so maybe maybe you on some diet program. Yeah, and we can look at maybe we should just say the amount of calories consumed versus the amount of weight lost. And we can see people who have consumed large amounts of calories, the amount of weight lost would probably be low. People who've consumed small amounts of calories, probably will be associated to larger weight loss. Okay, that's a good example. Maybe something as silly as the temperature outside and how many sweaters have been sold at a store, okay? So on days where the temperature is high, the number of sweaters sold, probably low. On days where the temperature is low, the number of sweaters sold, probably higher than average. Altitude and air pressure. Areas of high altitude will have lower air pressure. Areas of lower altitude will have higher air pressure. Okay, so those are all examples of negative relationships. Okay. And again, it's important that when we're talking about these things that both variables are numeric. So if one of the variables is not numeric, you're not going to have these positive or negative directions in relationships. Okay, strength. Strength of a relationship is a measure of pretty much how well can we predict one variable based on the other. Or another idea is how much scatter do we have? Scatter exists in the scatter plot. These are both informal definitions. But basically, if you have a strong relationship, you would have good predictions and little scatter. Good predictions. Little scatter. Weak relationship. Basically, poor predictions. And lots of scatter. More scatter. So a silly example would be if we measured someone's height in inches and we measured that person's height in centimeters, you would have a strong, or actually a perfectly strong relationship. If we know someone's height in inches, we can predict exactly their height in centimeters. Okay? And if we looked at the scatter plot, there would be no scatter because everybody would be lined up along the line. Okay, because we know your height in inches, we can get your height in centimeters very, very well. Okay? Something that is not perfectly strong, but will be very strong, will be maybe a shoe size, the length of your foot, and what size shoe you wear. Okay, so maybe we measure people's feet in centimeters or inches or whatever unit we want, and then we also ask what shoe size do you wear, and we'll see a very strong relationship. Okay. But it won't be perfectly strong. There will be a little bit of scatter because some people prefer to wear their shoes a little bit loose, and some people prefer to wear their shoes a little bit tight. So shoe size versus length of foot. Okay. And it's whichever one you want to use as your X and your Y. So we'll go with shoe size, and we'll say length of foot. And we'll see, let's say somebody has a size 9 shoe. We'll have a few people, and we'll probably see a little bit of scatter in terms of the length of people's feet who wear shoe size 9 or something. Okay. And if we look at shoe size 9.5, okay, we'll probably also see a little bit of scatter there in terms of the actual length of someone's foot. Some people, and so on, and so we'll have a little bit of scatter in our line here, okay? But overall, there would be a very strong relationship where we see people with shorter feet will have smaller shoe sizes. People with longer feet will have larger shoe sizes. Okay. So this would be very strong relationship. We'll have a little scatter. And we would say this is a positive relationship. A weaker relationship would be something like height, someone's height, and their length of foot, okay? In general, people who are taller have larger feet than people who are shorter. That's just a biological fact. But there's no one-to-one correspondence or anything like that. Okay, so overall, we will see a trend where taller people have larger feet. Okay, so if we're looking at height on the x-axis and foot length on the y-axis, we will see overall trend but there will be more scatter, okay? So you will have some tall people with relatively small feet. You will have some short people with relatively large feet. You can take two people that are the same height, and they will not necessarily, one person's foot could be much larger than the other person's foot. But overall, we will see a trend where taller people tend to have larger feet than shorter people. Okay, so this would be positive and a weaker relationship. The strength of a relationship and the terms we use there, those are all relative, okay? So in some cases, you might say there's lots of scatter or little scatter. In general, when you have, when you're dealing with people, you're going to see a lot more scatter than if you're dealing with robots. And so, it's strong or weak. These are all kind of relative in terms of the situation that you are dealing with. We have, to summarize the direction and the strength of a relationship, we have a statistic, and that statistic is correlation. Okay? So, just like the other statistics you've learned, correlation, or like the other statistics, is simply a value that tells us about the attribute that we're looking at. Okay, so other statistics you have learned are the mean and the median, or the standard deviation. These are all statistics. They're numeric summaries, but they're just simple numeric summaries for a certain attribute. You learned that standard deviation is a numeric summary for the amount of spread in a set of numbers. Large standard deviation means the numbers are different from one another. Small standard deviation means the numbers are quite similar to one another. It's a summary of spread. Mean gives you an idea of the center of those set of numbers. And likewise, correlation is simply a numeric summary that tells us about the direction and strength of a relationship. Direction and strength of a relationship. Again, between two numeric variables. Correlation is only meaningful in the context of a linear relationship. You find correlation with a formula, and so it's going to, correlation exists for any two numeric variables. You can calculate correlation for any data set where you've got two numeric variables. But the interpretations or the meaning that you can draw from correlation, it's only meaningful for a linear relationship. So it exists for any pair of numeric variables, but it's only meaningful for a linear relationship. This statistic for correlation is R, the symbol for correlation is R. And R can take on any value between -1 and +1. So correlation can be any value between -1 and +1 inclusive. And the sign of R is the sign of the relationship. So if R is positive, your relationship is positive. If R is negative, your relationship is negative. And if R is close to 0, is weak. And if R is far from 0, the relationship is strong. So R is positive 1 or 0.99 or negative 0.9 or whatever. Those are all strong relationships. R close to 0, so 0.1, negative 0.2, things like that. You've got a weaker relationship there, weak relationship. So R, or correlation, is just a statistic or a numeric summary telling us about the direction